Hello, thank you very much for your kind introduction. And I personally thank Lisbeth for inviting me to this exciting event and also for placing me in the center. Behind the scenes, I have to say, the more clinically oriented people should go here and the more technically oriented people should go here. So while I invite Matthew Hoptops and Nick Cummings, so Matthew here, Nick. I would like to say that this is a very important part of the morning because we are adding a level of complexity to what we have heard. Neuromorphics, thank you for this word, are frozen. So even though you add functional information like time information, they are collected in the lab, stored, and collected in intervals that are in the order of months. And now we have to face another level of problems, which is the interface with real people in their real life for an unlimited amount of time. And as Helena said, we have also to face the problem of how to interpret fluctuations and progression and think about the COVID infection and COVID restrictions are fluctuations. Fatigue from COVID could be worse than fatigue from a relapse. Many of us can tell that. And we have also to face the issue of burden on patients, psychological burden, but also aesthetic burden, as also Gavin was mentioning, and stigma. So this is something we have to address now. So many of all our speakers have several roles and won several grants, so I will just make a resume. Professor Hoptop is Vice Dean of Research at the Institute of Psychiatry, Psychology and Neuroscience at King's College London. And his role here is to address the issue of putting together the relationship between brain changes, mental changes, and big data. And Nick Cummings is a lecturer in artificial intelligence for speech analysis for health at the Department of Biostatistics of Health Informatics at King's College. And again, he's addressing something that could reduce burden because speech analysis could be performed passively. So avoiding people to think about their disease. So please, Matthew.
Well, thank you again for the organisers for inviting us. This is very kindly described as non-MS success stories. I'll leave it for you to work out whether it is a success story. And I'm going to talk about a program of work I've been involved in, I've been leading, called Remote Assessment of Disease and Relapse, RADAR CNS, which is an innovative medicines initiative program which has involved numerous centres. I will, as it is an IMI program, I'm obliged to put up the acknowledgements and disclaimer here, but also to acknowledge that it is a very large partnership which spans 9 different countries, about 23 different entities, 5 pharmaceutical companies, and just to prove it, this is our first meeting, not very far from here in Brescia. And you can see that we've aged, but also this was in 2016. In happy times for me, it was just before the Brexit vote, and I think a lot of what we've heard about today has been the importance of international collaboration and partnership, and as a Europhile Brit, it's very tough hearing about the wonderful things happening in Europe, which we are less able to participate in. So what is RADAR CNS? What's it about? So if you think about most healthcare, most of the time what you're dealing with are episodes of encounters with patients, either clinical encounters or with research participants in research studies. These encounters mean that you get sparse and episodic data. And that, of course, doesn't reflect real life. If you're an MS physician and you're seeing someone in clinic every 6 months or something like that, you're having to make an assessment about their clinical state over the previous 6 months, and you don't have very long to do it. So the aim of RADAR CNS is to use technologies to be able to give something which is far more continuous, pervasive, and using passive data as much as possible to span different stages of disease. So we're talking here about smartphones and wearable devices. We're talking about both active data, which people are inputting into those devices, but also passive data, which are just being taken off the devices all the time. And we're interested to see whether they have an impact in being able to tell us something about health. And if you look, this schematic here describes the problem. If you see the wiggly line is essentially disease severity. It could be, in my field, psychiatry, it could be symptom severity for depression. We have arbitrary cutoffs where we say someone has had a relapse of depression. And in the periods leading up to that relapse, there are potentially signals which may be identifiable and clues as to the fact that a relapse is happening, so you might be able to do something earlier. And that's essentially the motivation behind this. And the RADAR CNS program operates in depression, major depressive disorder, in epilepsy, and also in multiple sclerosis. But we're going to be focusing on the depression data today. So it's quite a big task, actually, to find a pattern in these continuous data. This is a real-life example with no AI at all. It's an anecdote, but I'll give you the anecdote. So you see here, this is an individual who has heart rate data from their Fitbit. It's a Fitbit charge, and it's the one I'm wearing right now. So this is my data, and you can see along the top there are 3 points where the heart rate was much higher than you might expect. I pride myself on being reasonably fit and having a low heart rate, low resting heart rate, but there are 3 points where it zoomed up. Were they anomalies? Were they something which told you something about my clinical state? Well, the first one spikes, and the second one spikes, and they look quite similar. The third spike is followed by a period of a reduced heart rate. So what was going on? The first one was the end of data collection for my part of the RADAR study, where I invited my research assistants round to my house and we drank too much champagne. And I didn't have a good night's sleep and my heart rate went up. The second one was my frustration with various colleagues whilst I was writing a large grant and I was trying to get back to them and I was losing sleep and my heart rate went up. And those, you could say, are just normal. They're ordinary events which take place in one's normal life. And there's no clinical relevance. The third point was when I developed abdominal pain. I ended up in hospital and I had my appendix taken out. It was gangrenous and it was nasty. And there you have another heart rate signal, which you might have mistaken for the other two had it not been for this dip afterwards when I was actually at home. I was being told to rest. I was actually having quite a nice time only doing the bits of work I enjoy doing. But the point here is you're trying to find needles in haystacks. It's a very challenging task actually finding an anomaly which means something and means something to patients. And what you don't want to be doing in this sort of work is having multiple false positives all the time, which will confuse matters. So what can we get from smartphones and wearables? Well, this sort of schema just gives you some of the things which we were interested, and I won't go through them all, but the effect is that actually out of these devices, you can get very different data, obviously, from gold standard assessments of cognition, gold standard assessment of sleep, but you can get something which approximates to some of those, which has the benefit of being ecologically valid. I mean, think about what a true sleep lab study is like. You're connected to EEG, you've got hundreds of leads on you, you're in an unusual environment, and compare that to what you can get out of a wearable device. It's different data, it's not gold standard, but arguably it has certain advantages because you can use it longitudinally. Similarly, if you think about neuropsychological assessments, which might take 2 hours of very intensive, and you can't do that repeatedly, you can't do it on large numbers, but you can glean information from smartphones which can tell you something about this. So in a sense, you have devices which are being used by most of our patients most of the time, which are potentially very powerful insights into a whole range of higher cognitive and behavioral functions. And this is really the kind of opportunity which RADAR CNS was trying to leverage. And Nick will talk more about this, but essentially when you've got you think about what the data are, you've got raw sensor data on the bottom level, and then as you go through from the raw data, you're trying to get some kind of meaning before you actually get close to having a biomarker. And that then creates effectively highly dimensional, highly complex data which you're trying to put together to make sense of your clinical state. Now, it's good to have heard from patients, people living with MS today, because one of the things we emphasize in the RADARS consortium was the importance of patient involvement in doing this sort of study all the way through. We had a very active patient advisory group, you can see them there. But at each stage of the research, both the design stage, the data collection stage, and the interpretation stage, we were really keen to be able to get very good patient involvement. And the reason for that is that if you're asking someone to get the data out of their smartphones and wearables, there are obvious issues about privacy. Will people be able to tolerate that? But also there are issues about interpretability. They can, in a way, tell you about the times when they've had a hangover, or they've the equivalent of a hangover, I should say. So those sorts of issues are really important to be able to understand. And running these sorts of studies, actually having a really close handle on participant experience, what they will and won't tolerate. So, for example, in the selection of wearable devices, it's absolutely critical. Some wearable devices which were more research grade were unacceptable to our patients because they saw them as being unusual. They had to be charged more frequently. They were seen as being obtrusive and would potentially add to stigma. So people really wanted something which was much more like a consumer-grade device, and in the study we're going to talk about, it was a Fitbit. And then you have building sustainable platforms. So we needed to build a platform. Many IMI projects start with that. And if you looked at what was available for mobile health, certainly 6 or 7 years ago, what there were a lot of closed source platforms which were often very much fitted to a particular technology, be it Apple or Garmin or Fitbit, and or to certain specific diseases or certain particular use cases. So they were sort of closed, they weren't widely available, they were very much sort of limited by the way in which they'd been established. And what we wanted to do is create something which was effectively pluripotent. You could actually plug and play a whole range of different devices into it, and also was open source. And the open source was important because that actually builds sustainability into the program. If you make it open source, you bring with you a group of other developers who actually use the technology. And so we came up with Radar Base. Website's there if anyone wants to look at it and develop it. And effectively what it does is it takes data from smartphones, and it can be used actually from other devices, Internet of Things, other API connections, but also via so wearable devices via Bluetooth into the smartphone's own passive data, and then also a couple of apps which we integrated into it, which were around collecting active data, and that then forms the main data lake, as it were. There's a capacity for real-time data analytics, you can see on the left, and the more traditional historical data analytics on the right, along with visualizations. So this was a tool which we built and has now been widely adopted in a range of other disease areas in mobile health. And one of the features which you probably can't see this very well, but one of the features is that if you're running a study like this, you want the researcher to be able to see what's going on for the individual participant. So you actually can have this sort of real-time in-study participant monitoring, being able to look at where the data's missing, but also to be able to look at the data itself. but there's a whole range of other dashboards which are available with this. So the RADAR MDD study, the depression study, aimed to do three things. It asked, the first question was, can it be done? Will participants actually tolerate this? And I'm going to talk a little bit about that in a moment. The second is, can it tell you something clinically useful? And can we predict depression relapse? And those points Nick will pick up on whilst also dealing with the data challenges. The state of the art when we started was that there had been some studies in depression on mobile health. Nearly all of them were tiny and only lasted 1 or 2 weeks. So they're very much kind of testing out whether the technologies meant anything at all, and they were typically on about 50 participants. So these were really too small to be informative and answer any of the questions we had. The other state-of-the-art issue was that there had been a number of kind of citizen health studies where people could onboard themselves into a mobile platform and then donate their data to the research team. But most of these studies were actually, had terrible half-life. So the participant engagement in the typical study was a sort of half-life of about 2 weeks, which again was going to be really uninformative for anything we wanted to do in terms of long-term disease monitoring. So in RADAR MDD, what we had was a group of participants with major depressive disorder. They'd had relapsing and remitting major depressive disorder. We followed them for 2 years. We did more traditional outcome assessments every 3 months. We then classified them on those outcome assessments into whether they'd had a relapse or no relapse over the time. And we used data from these different devices, both active and passive data, to be able to follow them over time. And, sorry, this has been lost slightly in the translation of our slide formats, but the first question was, would you be able to recruit people into this study? The simple answer was yes. Actually, once you'd got, we got to 623 people enrolled. The point was actually that of the 991 who passed the eligibility assessments, sorry, the 689 who are eligible for the enrollment, nearly all of them actually got enrolled. So participants liked this, and a lot of our qualitative work told us that that was the case. Secondly, retention. I mean, the key figure here is that about 80% of participants participated for the maximum period of time they were in the study for. So we had a slightly rolling recruitment process. We used data for as long as they would be able to give it to us, recruiting over a 2-year period. So some people were in the study for a shorter period than others. But if you got into the study, you stayed in the study. 80% of people stayed in the study, effectively. Now, this is the challenge, in a way, is the nature of these data. So this is the availability of data over the course of those 2 years. And what you can see is a number of active tasks, and actually a high proportion of people are giving data at least 50% of the time, or 50% of the data points we wanted. But you do not get complete data in these sorts of studies. And there are all sorts of technical reasons for that, but it's just the nature of the beast. You do not get complete data. So we've been hearing about data quality and biomarkers and what it's like for getting your MRI protocols all lined up. But in this field, it's going to be very difficult to get data of absolutely the quality one would like it. So the main thing I wanted to say in the first aim was that recruitment was easy, retention was good, and data completeness is variable and sometimes outside of our control. I haven't mentioned participant satisfaction, but the satisfaction was on the whole very good. I'm going to hand over to Nick, who will take us through some of the technicalities.
Thanks, Matthew, and thanks to all the organisers for letting me speak here. So one of my roles on the project was actually helping with data organisation. So as Matthew said, we collected a lot of data from a lot of people over quite a length of time. And the first big problem we had with this was the multi-parametric nature of the data and the temporality of the data. We were collecting data points in terms of milliseconds to months. And we somehow had to combine all of this data through numerous people with numerous conditions into a database that could be used by the clinicians, could be used by the technical teams to actually empower the study. And within this, we also had a lot of missing data as well. So we had to find quite a lot of different ways of handling it, how to combine everything together. So we had the data sources, we had the platform in place, then we had to sort of organise all of this. We had to do quality checks, we had to do all the signal processing involved, and essentially start to aggregate the data. And we didn't have any guidelines, anything to go on, so we sort of aggregated on a day level because that seemed about reasonable to us. And I mean, there's still this fundamental question and assumption we made very early in the project needs to go back and be revisited and start the whole process again. So these are results of one of N results that we can possibly do here. And of course, then we had to summarise in terms of the different clinical outcomes, and a lot of different things had to come together to enable the sort of data analysis. And we ended up coming up with a squilled data set that really had quite a lot going on in terms of organising the different passive and active data streams into their own tables, having different lookup tables, having different metadata associated with everything, so we can sort of come in, you know, make a query on the data. I want data from time period A to time period B on this data stream from these participants, this sort of gender. We can allow different queries, different ways of looking at the data, and it's all sort of findable within the Squill data set. And this actually took a substantial amount of time, a lot longer than we thought, to just come up with this structure. And even trying now to implement it in other projects using this is just a big challenge of how to tailor these into different projects to make sure that data is findable, data is usable across these. But we did manage to get this working. Here's just a little example of data from the Fitbit Sleep. We're able to organise and extract a lot of different features relating to sort of quality, stability of sleep. We're able to sort of come up with big definitions. Everything's there, everything that we need as data analysts, anything the clinical guys needed, all definitions, everything comes in. And it worked. We were able to do some statistical analysis on the sleep data, and it's always nice to get results that you expect. We found that as depression increased, people's awake time in sleep increased. They had an increased variance in sleep, the sort of duration, onset and offset, all varied. Sleep quality reduced, there were more days with insomnia, more days with hypersomnia. So this was really good. We were able to record data in the real world, measure it against a clinical outcome, and actually see a result that we expected. So this was a big sort of win for us, being able to go, yes, remote monitoring, using commercial devices, using our platform does work. And here's just a little example of a PHQ-8 and sort of sleep measures about it from, you know, one of our more exemplar patients within our group there. But the real power from this data doesn't come from just one single data stream for one person where you're going to have a lot of false positives. It comes from trying to put all the data together and try to find the needle in the haystack that is a relapse event for all of this. And this was actually really even a harder job than we thought. And one of the things that I guess we underestimated more at the clinical end of it was how rare relapse events were going to be in an observational study. So we had 623 participants in the study, had them in the study for almost 2 years, taking into account that we associated relapse every 3 months. We had 59 relapse events. That's not much that is actually happening. So we've got a lot of data, but not very many relapses. So how do we actually set about doing this? How do we solve this as an AI problem? So with relapses being a sparse event, we thought we can't do classification. We can't sort of go, is it a relapse event? Is it not a relapse event? We simply don't have the data distribution to support this. We're not going to be able to do it. We're going to have, well, the curse of dimensionality that was sort of spoken earlier. There are blind spots all over this data. There's things we can't do. Just not enough data in the minority class to train a classifier. So what we thought is we'll actually have to do something like outlier detection. So we'll make a hypothesis that a relapse event is going to occur as something different in the data streams. Something's going to change, something's going to happen. The distribution of data is going to vary at some level. How do we go about, how do we assess finding this? And the way we came about with doing this was using a technique known as autoencoders. So autoencoders are a neural network designed to recreate the input data. So essentially all we do is feed data in at one end, we squash the data down, we try to make it a very dense vector that contains all the vital information and throws away all the noise. And then we try to rebuild from there. And this is not that hard to do. We can sort of construct these vectors where we measure the input data, squish it down, reconstruct it, and then essentially measure the difference between the input and the output of these, just using something like Euclidean distance between the two vectors that you're feeding in and that you're feeding out. And you try to minimize this. And this works really well and enable us to sort of do outlier detection, because what we can do is take multiparametric data, train an autoencoder on non-relapsed events, and we begin to then learn essentially what the probability distribution of a non-relapse event looks like. We're then able to take this and test it on data that contains relapse events and non-relapse events, and we look at the reconstruction error. So what we really hope to see is that a non-relapsed event is going to look different, so we can't reconstruct its output from the input due to the big differences in the data between the relapse and the non-relapsed events. I hope everyone sort of followed me through this. So what you can see is this sort of idea of reconstruction error, and we put a threshold here, and you basically go, a high reconstruction error is more likely to be a relapse event, and then we've just got to play a little bit around with thresholding to get this right. To give ourselves a little more sort of sensitivity into it, we actually put it in line with active assessments. So we basically took one of our data streams, did our anomaly detection. If we detected an anomaly in a particular month, we then looked at the PHQ-8 score nearest to that anomaly, did it meet the criteria for depression, did it not meet the criteria for depression, and define that as sort of relapse and not relapse. So we were able to sort of combine both the passive and the active data into one stream. How did we go? So first up, looking at just passive data, looking at individual data streams. The two columns really to look at here are the specificity and the sensitivity. And you can see that we had high sensitivity but low specificity looking at these individual data streams, which doesn't surprise us a little bit, but it sort of shows that individually there's some information coming through, but we definitely do need to combine them in a more multimodal analysis. When we combine it into a multimodal analysis, specificity goes up, sensitivity goes down. When we added in the PHQ-8 scores, we get a little bit more of an improvement. Looking at different time windows makes a bit of a difference. We're still sort of analysing, pulling all this apart, but it's quite a sort of tricky problem to get the balance of everything right. I think this sort of approach of autoencoders, outlier detection is the way we've got to go. We've just got to get a bit more fine-tuned with it. When we do an evaluation on personalised models, so just training a model on an individual and using their next month's data to test the models, we see a little bit better results. It certainly shows that these models are probably more personalisable and less generalisable. So yeah, the challenges that we addressed, we got good generalisability, but only at a personalised level. We've still got this problem with trying to realise what non-relapse events are. We can only really train on this. We can only see what's going on there. And we've got this real specificity, sensitivity trade-off. I do think these results are really promising, though. We're getting results clearly above chance level. There's definitely signal in this data. It is a matter of learning more about the best ways to combine the data. So I'm just going to leave that there, just in time.
Thank you so much. You both have demonstrated that a lot of human work is needed to to interpret artificial intelligence results, because artificial intelligence is a human product. So it's requiring a lot of human effort to distinguish intelligence from stupidity. So this is really important to do. And you addressed both two different issues, but I have to disclose that I have been working with both of you for the MS cohort, and so we had to face some technical challenges and also some human factors. And among the technical challenges, we are still in a developing field, as, for example, in the inclusion criteria, there was the willingness to use Android, and so we also need to interface with different technology. But also, the idea of adherence was very important, because active tests are important to hear patients' voice, but people don't want to talk about it all the time. And the passive is not going to solve the problem completely, because we have to face the issue of feedback. People want to self-manage, and would you address the issue of feedback of the results to the patient who owns the app?
Feedback wasn't part of our original protocol, and that was deliberate because we didn't know the quality of the feedback which would be possible. So I think at the moment we're working with patient groups looking at kind of visualizations and what they would like to see and that sort of information. But this was it felt too early to be able to do it. Certainly when you asked our focus groups, people loved the idea of the technology for a number of reasons. One being that they would be able to see and in a way own their own data, be in control of their own data, and be able to take it to a clinician and be able to say, look, this is the reality of my condition. So I think, but for this particular project, we didn't go there.
Mm-hmm. So there's a lot of work to be done. And about the algorithms, are you happy with the algorithms developed, or are you still working on them?
I'm happy with the general idea of the algorithms we've developed, the idea of that essentially we need to, most of the data we collect is probably uninformative, not much change is happening on a day-to-day cycle, and we've just been spoken about this morning in the MS. But yeah, how do we find these really informative bits? How do we find these big points of change? How do we discover that Matthew's about to go to hospital? How do we find these? And there's a lot of things happening in the data, and we've still got to find that, combinations of things. We're very naive here, and I think we need to move away from classification and move towards more unsupervised monitoring, where we're realizing these difference in probability distributions, multi-parametric probability distributions that are RMT data.
So thank you very much. So you're really proving that a lot of human work is needed. So thank you very much, and congratulations for your successful enterprise.